welcome to my favorite topic on fractals. Even though it's my favorite, this is actually going to be one of the shorter videos. I was going to introduce fractals to you, but I'm going to leave it up to you to do some of your own research and go out there, and because there's a lot of awesome videos and things available online to watch that can show you this way better than I can. And then you also have a project that's going to have you exploring this concept. All right, fractal geometry. We can thank Benoit Mandelbrot for this kind of geometry. He is the father of it. He was able to develop this kind of geometry to help explain and use mathematics to talk about objects that are of a fractured nature. And it's very real world, very applicable to life. There's fractals being utilized in ways that you don't realize in your everyday lives, and you'll find out in a minute just how that is. All right, what are fractals? Fractals are objects that exhibit self-similarity. In other words, they're made of these repeating patterns that as you zoom in, you can't tell how far you've zoomed in. They can be generated using a process called recursion, where you start with a baseline, like a shape, and then you just keep applying certain rules over and over and over again, or certain algorithms over and over and over again. And eventually you end up with this very complex figure just by doing these simple rules. It doesn't take much, it just takes maybe one or two rules. And then it's the idea, though, of doing it over and over and over again. Ideally to infinity, but in real world, it's not going to go to infinity. There's going to be limits on it. Some examples of fractal objects are things that some you see and some things might have never seen. In fact, mountains like the Rocky Mountains, I first saw those 2 summers ago. That was my first time, but I'd seen the Smoky Mountains, and you see pictures. Mountain ranges, rivers, especially if you're like flying up in the air or in a drone or something and you look down at a river, it's a fractal shape. Snowflakes, we don't really see those much here in Florida, but they're a fractal image. But we do see coastlines. The example they usually use, though, is the coastline of Britain, like looking at its shape. And we see a lot of lightning here in Florida, especially if you're near the Tampa area. Those are all examples of fractal images. If you think about like lightning, I mentioned that one because we're in Florida. But if you think about when you look at a lightning bolt, it's a very zigzaggy type structure, and there's usually these little branches off of it. And the branches have branches. And if you were to be up close when lightning struck something near you, if lightning is to strike something near you, it's going to look like the full lightning bolt just hit. But in reality, you probably didn't see the whole lightning bolt. You probably just saw one little branch of it. But that small version, it's kind of like you're zoomed in. That small version looks like a whole lightning bolt. And no matter how many pieces you break off, it's still going to look like a lightning bolt. It's still going to have that certain characteristic pattern to it. The same thing goes with certain trees too. Like if you think about a tree and how it looks, I think about oak trees. I used to have a big oak tree in my yard. And the oak tree had, you go up, you start seeing branches. And during a bad storm or something, I would definitely have branches that fell off. Or I'd have to regularly go out and trim my branches because the tree was near a street, and you'd have to make sure they weren't, hanging over power lines in the street too much. But when I would trim my branches and then drag them out to the side of the road for the trash to come pick up, those branches alone looked like little trees. Like if you just took one branch and took a picture of it, you had no way of knowing whether that was a baby tree or whether that was just a branch. Because trees also have that self-similarity, as you're looking at smaller pieces. And you can take plants, and many of them, and you can do cuttings where you can take little branches and you can indeed sprout roots on them and start a whole new plant. So that those little pieces, it comes to mind, I am Groot, you know, in the Marvel universe there. It just needed that little tiny sliver, but under a microscope it might look like a tree, you know, might look like Groot. And then as they nurtured it and cared for it, it could grow up into the bigger tree, but those little arms and stuff still look like smaller trees. So that's examples of some types of fractal objects. And then, you know, if you wanted to create them, like let's say you're working on creating a movie in graphics and you wanted to make trees that looked realistic, you have to use recursive process, where you have a basic shape provides your starting point, and then you start applying your rules to get a new self-similar shape. And each time you apply the rule, that's called an iteration. The rule is applied again and again. Mathematically speaking, it should be applied forever to infinity. Realistically speaking, you just apply it enough to get what you need. One of the videos that I suggest later that you watch talks about in one of the Star Wars movies. They were fighting with over a bunch of lava, and the lava is like splashing up all around them. And they used fractal techniques to help create that realistic looking lava. So obviously the actors aren't actually fighting over lava that's splashing everywhere, but they were able to start with some basics and apply a recursive process over several iterations and make that lava. For our purposes, let's just look at one that's not very natural, but it's pretty cool looking still. Let's look at one called Sierpinski's gasket or Sierpinski's triangle. Named for Wacław Sierpiński. One of the cool facts about him was he has the same birthday as Albert Einstein. And both of them have their birthday on Pi Day, March 14th, the American Pi Day, March 14th. In Europe, it's a little different. They do their dates differently. But here in the U.S., that 3/14. So that's kind of cool. But anyways, Sierpinski's triangle. At iteration 0, you would start with just a regular blank triangle. And the rule for this is that you would, at iteration 1, the rule is you take midpoints at that available triangle and you connect them. And that looks kind of like the Triforce from the old Legend of Zelda games, right? For those of you who played those. But that's the beginnings of what we're going to have here. And you can color that in. And now that you've made that new triangle, it's no longer available to work with. But that's iteration 1. So that's the first time applying the rule. Second time applying the rule, we just keep going from what we already have. So we already have the Triforce thing. Then we have these remaining triangles that we didn't draw in yet. So we're going to do the same rule. We're going to take whatever the midpoints are of the sides and we're going to connect the dots. And then color it in. Those are no longer available to use. So that's iteration 2. Iteration 3. It's going to start getting a little more complicated now, isn't it? At iteration 3, all right, we have what we already had in iteration 2. That hasn't gone away. And forgive me, I'm not doing this very exactly. Like on your project, I ask you to use a straight edge and measure things, make it nice. Don't just freehand it like I'm doing. I'm just doing this for the sake of this video because I don't think you want to sit here and wait while I pull out my ruler and get all exact on you. I'm just trying to demonstrate the concepts here. So iteration 3, you have these extra, these white triangles still. you're going to connect the dots on those midpoints, on the midpoints of the edges. So notice that each time my triangles are getting smaller in this particular fractal. But notice now, you can start noticing now that each time I'm basically creating the same pattern over and over again. It's just that pattern, they're getting smaller and smaller. And eventually this will get so complicated that I'll be able to zoom in on any piece and still see the same pattern. So iteration 4, the thickness of my pen is going to make this really hard. I'm probably not going to be able to do much on iteration 4 with the thickness of my pen. But if you were to do something like this, like for a project, you'd make it bigger, use a sharpened pencil or something. Give yourself more space. I'm trying to squeeze mine in here. So it's noticeable that I'm running out of space. But that's the beauty too of the infinite nature of fractals, is that it doesn't matter how small you go, how much you start zooming in, you're going to keep uncovering the patterns still over and over again. So that's where the zooming really helps. And fractals fractal concepts could be thought about before computers, but thankfully during the time of Benoit Mandelbrot, he worked for IBM, he was very familiar with computers. He was able to use computers to help generate images and help work the iterations, multiple iterations of these equations, so that he could get good representations of what was happening. So it really wasn't until computers were widely in use that we could really start to develop fractal geometry. So he did that. He faced a lot of ridicule. If you look at one of the videos I suggest later, talks about his beginnings and how much ridicule he faced and all that from his peers in the mathematical world. Higher education or higher research and stuff can be full of politics. And if people don't like what you're saying, they'll make fun of you left and right. It doesn't matter what PhDs you have. But anyways, so he faced that, but he persevered, and thankfully he did, because we are able to do all kinds of things with these wonderful shapes. So you're starting to get the idea now with iteration 4. Like if we were able to take this and start zooming in, like if you zoomed in on this piece right here, the image that you would see there looks just like this image here. If you just zoomed in on that piece looks identical, but yet they're not the same. Remember, the one with the arrow was iteration 3, and the one with the triangle around it, iteration 4, is a piece of that. So, but that's the whole idea of the self-similarity. Zoom in, see the same thing. Pretty cool, huh? There's a lot of, again, go online and look for like fractal images or fractal zooms, and you'll be able to find some cool videos where they have computer generated fractals and then they start zooming in on them and you can truly see what's going on. The Mandelbrot set is one that is really pretty. That might be one to search for. Yeah, so go online and like search for Mandelbrot set, fractal zooms. You can find a lot of stuff if you do that. Julia set, that's another one. If you search for videos for those, you'll come across some things that'll really show you. So again, fractals, you can't really tell the size of them since they look the same no matter how far you're zooming in or out. They call that scale independent. So it's no matter what your scale is of the image, it's going to look the same. So they have geometric structure that provides a way of describing seemingly chaotic processes in the natural world. So suddenly things that seemed too chaotic to use Euclidean geometry, now with fractal geometry, they were able to start talking about them in mathematical terms, and all kinds of areas like meteorology, medicine, geology, chemistry, all kinds of fields. Some particular applications, like they're in Central Florida, Disney Wilderness Preserve. I used to live not too far from that when I was in Poinciana. And it's not terribly far from Winter Haven, but it's in Poinciana, closer to Kissimmee. But they some scientists from UCF were able to use fractal techniques to study the forest canopies there in the Disney Wilderness Preserve. And the fractal techniques were able to tell them which parts of the forest were healthy and which parts might be facing disease. There's a technique called the box counting technique, which I'll briefly mention in a minute. My graduate thesis advisor, he had worked with some middle school kids who were able to take EKG readouts. And they were able to apply some basic fractal techniques to help decide if a heart is sick or healthy using the EKG readouts. If you do watch the movie Fractals, The Colors of Infinity, if you do watch that, or no, Fractals Hunting the Hidden Dimension, I'm sorry, that's the PBS one. PBS has a whole video. If you go online and try to find that and watch it, it talks about how antennas in things like your cell phones are actually shaped as fractals, because then they're able to, instead of having multiple antennas sticking out of your cell phone, they're able to have one to receive all the signals they need to receive. Another thing was like when trying to do sleep studies and studying brain waves and sleep patterns, you can use fractal techniques to help see if you're getting a good night's sleep or not and see what's happening to your brain while you sleep. So those are all some different examples. I mentioned the box counting technique. That's something that uses a little bit of some algebra and I don't know why I said box fractal. I was thinking about fractals. I'm trying to write this. That's what I get for talking and writing at the same time. But the box counting technique can't even spell correctly right now. Goodness gracious. That's what I get for trying to do too much all at once. Like we were talking about the EKG readouts for the heart. No, this is not an EKG readout. I'm just doing some squigglies like what I think it might, kind of look like. But what they do is they take a grid, like a piece of graph paper, and they put it over the EKG readout. Or they also did this with the forest canopies, and they do this with all kinds of different studies. But then they apply some probability techniques in certain kinds of math equations to look at the probabilities of pieces of the EKG being found in certain boxes. They'll look at a bigger grid, and then they'll go from there and make a smaller grid and start looking at what's happening, statistically across these smaller boxes, and then they'll do another smaller grid. And they'll keep applying this analysis, probability and statistics, but it also intersects with fractal techniques, with fractal math, to start looking at, likelihoods of different pieces of that EKG being found in what parts of the grid. And those numbers they're able to generate using their algorithms helps them to determine, what's the likelihood of this heart being healthy versus sick? Or what's the likelihood of this forest canopy being a healthy trees or sick trees? That kind of thing. So if you want to learn more, there's several TED Talks. There's one with Benoit Mandelbrot in it. He only passed away several years ago. When I first was teaching this class, he was still alive. So that was kind of cool that they had a chance to do a TED Talk with him before he did eventually pass away. So do a search for that. Watch that. That's really neat. And then if you go online, PBS is not streaming their Fractals Hunting the Hidden Dimension, but they have a whole website devoted to it. I put a link in our modules for it. And then you can also find websites that do have it up there. I really encourage you to watch that movie. Find it and watch it. I can't post it here, copyright reasons and all that, but I told you the title, so I'd say go find it. You learn a lot about fractals and it has some really cool imagery and everything there. Way better than I could try to do in this video with you. Fractals, The Colors of Infinity was another one that we used to watch years ago. That one was on VHS tapes. I don't know if you can even find that online anymore, but you can search and see. But if you watch any of them, watch the one from PBS. And that one has a lot of resources online too. Or even if you don't get a chance to watch it, you can find the transcript there on the PBS Nova website. It's a Nova movie. All right, so that's some of the big things with fractals. I was trying to think if there was any other examples to throw out there. There's a ton of examples to throw out there. You talk about it a little bit in your books, but you know, I really can't do it justice on here. So yeah, so go out and search, have fun, and thank you for joining me. I will see you again soon.